Hello, welcome to the design of reinforcement concrete. We are now at CO5 and session number 48. The course outcome is design and detailing of lintel problems. The earlier sessions we learned how to design the lintels. In that there are two cases, how to consider the load from the wall above it. So first cases was related to the load wall is behaving in the form of triangular load, and also we discuss if the chedja is also connected, how to design the lintel. So today in this session we're going to learn about how to solve the problem on lintel which the dead load of the wall above the lintel is behaving as a case 2, that is uniformly distributed load. So we need to identify when it will become a uniformly distributed. The wall which is above the lintel will behave as a uniformly distributed load. So problem, the design of lintel on an opening 2.4 meter on a 230 thick brick wall. Height of the brick wall above the lintel is equal to 1.5 meters. So this is the 1.5 meter, which is the wall above the lintel. The concrete we are adopting as M20 and Fe steel as Fe415. And weight of the concrete is 25 kilonewton per meter cube, and weight of the brick wall is equal to 19.2 kilonewton per meter cube. And at the end, we should also sketch the reinforcement details. So the given, as we seen in the problem, the span was 2.4 meter. This span was 2.4 meter, and the height of the wall above the lintel from here to here, it is 1.5 meter, and thickness of the wall is 230 mm. In the other direction, if you are able to recollect, the bearing is equal to 230 mm, and type of the concrete is 20 Newton per millimeter square, and steel is 415 Newton per millimeter square. These are the characteristic strength of the material. Then weight of the concrete is 25 kilonewton per meter cube, and weight of the brick wall is 19.2 kilonewton per meter cube. So as usual, the first step is assuming a effective depth with respect to span to effective depth ratio. I am taking it here as L by D as 15. So once if you substitute the span 2400 meter divided by 15, we'll get 160 mm as the effective depth. We need to calculate overall depth. To calculate the overall depth, the capital D, it's required effective depth plus effective cover. So in this problem, I'm taking D as 160 and effective cover as 30 mm. Effective cover is nothing but nominal cover plus half of the diameter of the main reinforcement. So totally the overall depth is equal to 190 mm. So say 200 mm. Therefore, overall depth is equal to 200 mm. Then width of the lintel is equal to the width of the wall. That is, thickness of the masonry is equal to 230 mm. Then we need to calculate the effective span. The effective span is equal to center to center distance between the supports, or clear span plus 1 effective depth. So as per these two conditions, clear span is 2.4 and the bearing is 0.23. So it will equal to 2.63 meters. And second one, clear span plus effective depth, that is equal to 2.4 plus 0.17 is equal to 2.57 meters. So comparing these two, whichever is less means effective length is equal to 2.57 meters. Load, and once if we obtain the effective span, we need to calculate the load on a and moment calculation. So as we observed, to identify whether it is a triangular load or the uniform load, first of all we need to calculate what is this H. Then we have to compare this H. If this H is greater than H plus greater than 1.25 times of h, then it can be treated as a triangular load. So this only we are going to verify now. So height of the wall above the lintel h is 1.5 meter. So we need this height, that is height of the triangle, is equal to LE into sine 60. That is 2.57 into sine 60. We got a 2.22 meters. Here only we come to know that this height h is more than this, but even then we need to calculate as per the procedure. 1.25 times of h is equal to 2.775 meters. If we compare these two, we'll come to know that h is less than 1.25 times of h. That's why we can say that it will not be a triangular load. This wall which is above the lintel, it will not behave as a triangular load, it will behave as a UDL. Therefore, hence the masonry load W is UDL. So now we got a rectangular box, that is the height of the wall above the lintel. So this load we have to consider. So this wall which is above the lintel behaves as a UDL. So we need to calculate what is the total load in the form of UDL. That can be calculated by multiplying height of the wall, multiply by thickness of the. That means we need a volume of this multiplied by the density. So that is equal to H into T into density of material. This will not going to multiply because we need a load in the form of UDL. That's why we are getting we are multiplying only height into thickness with the density of material. Therefore, height is 1.5, thickness is 0.23 and density is 19.2. This total is equal to 6.624 kilonewton per meter in the form of UDL. So in this problem, the load on the load from the wall above the lintel will be in the form of UDL. So as we know, if it is a UDL, then the moment due to the load is equal to in the form of WLE square by 8. So substitute the values and obtain the value of M1. That is the moment due to the wall above it. Next, we also calculate the self weight of the lintel. So as we already know, the self weight of the lintel is in the form of UDL. So that is equal to breadth into depth, that is a cross-sectional area multiplied by density of the concrete. So we'll get a breadth into multiply by depth into density of material. We are getting 1.15 kilonewton per meter. So once again, the moment due to self weight, that's where we are referring as M2, and it is also UDL. That's what W into LE square by 8. So if you substitute the values of self weight multiply by the effective span, we are with the value of divided by 8, we are getting M2 is equal to 0.95 kilonewton per kilonewton meter. So ultimately, we required a total bending moment. So total bending moment is equal to M1 with respect to the wall above it and M2 with respect to the moment due to self weight. So total moment is equal to 5.47 plus 0.95, 6.42 kilonewton per kilonewton meter. We need ultimate moment. Ultimate moment is equal to factor of safety multiplied by the moment. That is equal to 1.5 to 6.4, 9.63 kilonewton meter. Once we obtain the ultimate moment, now we need to calculate the check for the depth. So check for the depth. For that we are equating moment of resistance equal to ultimate moment, that is equal to factored bending moment. So that is equal to ME equal to K FCK BD square, and K is equal to 0.138 or is equal to 0.14, since we are using Fy as 415 Newton per millimeter square. So we need depth, that's why D required is equal to under root of mu by K FCK into B. Substitute the values of moment, then constant, then value of FCK and B. We are getting 125.6, maybe we can call as 130 mm. That is a D required, but the D provided is greater than the D required. So I can say that the design is safe. If not, you have to redesign the depth. Once we obtain the depth, next step is we need to calculate the amount of reinforcement required. that to provided in the tension zone. So design of tension reinforcement can be obtained. In the earlier problem we have discussed by conventional method. Now we are using by SP16. So we have mu by, we need to calculate mu by BD square. So mu is equal to moment, ultimate moment divided by breadth into depth square is equal to 1.39. By using these values, we have to go through the SP16 from table number 2, which is respected to the Fe415 steel. So there we'll get a PT, percentage of tensile steel, is equal to 0.426. And as we know, PT is equal to 100 AST by BD. So since we know the PT, so AST is equal to PT into B into D into 100. So if you substitute the values, that is 0.426 is the percentage, B is the 230, depth is 170 mm. So divided by 100, we are getting AST as equal to 166.56 millimeter square. Providing 10 mm diameter bars. So area of one bar is equal to pi by 4 into d square, that is equal to 78.5 millimeter square. So number of bars is equal to total AST divided by small AST. So we are getting 2.16. So you may say it is as a 3 number of bars. So provide 3 numbers of 10 mm diameter bars. So this is related to flexural conditions, that is bending moment design consideration. But next we'll go for the shear. So design of shear reinforcement, we need to calculate first what is the shear force. So we have already two steps, two loads. One is due to dead load, another one is due to wall above it. So both are in the form of UDL. That's why we can calculate separately, or we can do it by adding both the loads. So by doing this, adding the two values, calculating shear force per individually, we can get the values. Shear force is equal to 9.98 kilonewton. Then ultimate shear force is required for analysis of limit state method, design of limit state method. So V is equal to 1.5 is the factor of safety. We are getting a value is equal to ultimate shear force is equal to 14.98 kilonewton. So this is the force. We need to calculate the stress, that is shear stress, or you may call as a nominal shear stress, that is equal to tau V, Vu equal to Vu by Bd. So once if you substitute the values in this equations, that is Vu, B and D, we are getting a value in shear stress or nominal shear stress as 0.383 Newton per millimeter square. This we need to compare with the design shear strength of the concrete as a TOSI. So to obtain the TOSI, we need to calculate first percentage of steel. So to obtain percentage of steel, we need to get area of steel which is provided for the flexural condition. That is 100 AST into BD will get a percentage of steel. So 100 into area of steel provided divided by breadth into depth, we are getting a 0.6 percentage. So now with the help of table number 19 of IS 456-2000, we will going to calculate what is the value of TOSI for the percentage of steel as 0.6. In this we know from the table for 0.5% TOSI is equal to 0.48, but we required for 0.6. So next value we have a 0.75 percentage, that is TOSI is equal to 0.56. So in between these two values we have a 0.6. We need to interpolate. If you interpolate, we are getting a value is equal to 0.51 Newton per millimeter square. Then once if you obtain the value of TOSI, this TOSI is compared with the nominal shear stress that is called as tau V. Since the tau C is greater than the tau V, that means the strength of the concrete is more than the nominal shear stress. That means we need not to design the shear reinforcement. The shear is taken by concrete alone. Hence provide nominal shear reinforcement. So design to provide the nominal shear reinforcement, we are providing 6 mm diameter bar, 2-legged stirrups. That's why the area of one stirrups is equal to 2 times of pi by 4 into d square. That is 56.55 millimeter square. The area of 2-legged stirrups. So we need to provide them in the form of spacing. So spacing of stirrups should be list of the following three conditions. The first one is spacing 0.87 Fi into AS divided by zero point 0.4 into B, that is for nominal spacing, that is equal to 0.87. Here we are putting Fi is equal to 250 multiplied by area of two-legged stirrups divided by zero point 0.4 into 230. So we are getting a spacing equal to 133 mm. We can say it is as a 130 mm. And second condition, it should not be greater than 0.75 times of D. That is 0.75 into 170, 127.5. Then SV should not be greater than 300 mm. So now we have 1, 2, 3 cases. Comparing these three cases, whichever is the less, that we can provide as a spacing for the stirrups. So therefore, provide 6 mm. There are two-legged stirrups about 125 mm center to center. So once if you design the section, depth, breadth and all, and the main reinforcement as well as the shear reinforcement, we need to sketch the reinforcement details. Therefore, first one is main reinforcement 3 numbers of 10 mm hash and hanger bar 2 numbers of 8 mm hash, and shear reinforcement 6 mm dia, 2-legged about 125 mm center to center as a spacing. So this is my section, and this is called span, what he has mentioned the problem, and this is a bearing, and this is the depth of the member, and this is the width of the member what we have designed. And first one, the main reinforcement 3 numbers of 10 hash, here also 3 bars. Then we have a 2 hanger bars, extra bars to support the stirrups. So that's all provided in the section. Then we have a shear reinforcement. You can also see that shear reinforcement which is surrounded by the main reinforcement as well as the stirrups. They are provided 6 mm dia, about 2-legged stirrups, about 125 mm center to center. So in this problem, we are done the design for the lintel which is subjected to a wall which is coming over it is behaving as a UDL. So totally we have two types of problem in the design of lintels. One is with respect to the wall which is coming over this lintel is behaving as a triangular load, and the second type of problem is the wall which is coming over the lintel is behaving as a UDL. So these are the two types of problems which you may face in the which may comes in the day-to-day life. So these are the some of the references which I referred to prepare the content. And I'm very happy to thank all my colleagues, civil chair, civil board chairman, moderators, and all subject experts, and all my colleagues who have put their effort to develop the content. Thank you one and all.